from yesterday, I just want to point something out. This is an example that we did yesterday, right? Dealing with the fundamental theorem of algebra here. So we had an equation, a quadratic equation in standard form, and we solved this because we couldn't factor it. We couldn't point to a single x, so naturally we used the quadratic formula. That's our strategy, right? Okay, look what happened here. We ended up getting answers that looked like conjugates, didn't they? Everybody see that? I've got 1/2 is the first term, and then the second term is 3 square root of 5 over 2. It's plus in one case and minus in the other, negative in the other, right? So those look just like conjugates. Why did that happen? Well, it happened in this case because when we used the quadratic formula, look what happened. We got a square root. We got a number inside the square root. So the radicand, number inside, was not a perfect square. So we were stuck with square roots in our answer, right? Anytime we get stuck with square roots in our answer and we're starting off with our polynomial equation it has rational coefficients. So no square roots as coefficients, no weird irrational numbers as coefficients. This is always going to happen. We're always going to see this trend. If we get stuck with a square root in our answer, it's always going to be part of a conjugate pair every time. And that was what we called the irrational root theorem, right? Just told us if we had rational coefficients and we get a square root, they're going to be, the square root is going to appear in a conjugate pair, okay? All right, so now today we're moving on to I'm plugging in one other important but pretty simple theorem, and it's one that you guys already really know. The factor theorem, right? The factor theorem just says this. If I start off with something like, let's say I factor a polynomial, a quadratic polynomial, and I get x minus 1 times x plus 2 equals 0. What are the solutions? What are the zeros of that polynomial? Yeah. Right? Everybody see that? Okay, that makes sense, doesn't it? So we knew that if anytime we apply the zero product property, anytime I have a factor, that's always going to give me a 0 also, right? So Tuese, what do you think here? Tuese, you're not getting enough sleep, buddy. You got to get more sleep at night. Could we turn this around and go the other way? We could, right? There's nothing to say that we have to start with the function and factor it and then come up with the zeros. We could flip this around and go backwards, right? Anytime that we know we have zeros of a function, we know that those zeros have to correspond to factors, right? That's what the factor theorem says. The factor theorem says if k is a 0, then x minus k is a factor. And if and only if means it's like it's like an arrow with 2 arrows on it, like a double-sided arrow. It just means you can start on the left and go to the right, or start on the right and go back to the left, right? Those two conditions always go together every time. K is a 0, then x minus k is a factor, okay? Now we use these terms. I want to just spend just a second on this too, some terminology. Root and 0. What's the difference? Some of these problems say root, some of them say 0. They're pretty much interchangeable, pretty much like just synonyms. But there's one small difference. If you want to be very specific and particular about this, a 0 relates to a function and a root relates to an equation, technically. Is it a big deal if you mix those up? Not at all. But we would say, for example, that if we have the function f of x equals x times the quantity x minus 2, then zeros of that function are 0 and 2, okay? Now, if we have the equation x times x minus 2 equals 0. So we're actually setting the function equal to 0 and forming an equation. Then we would say that 0 and 2 are roots of that equation. See what I'm saying? So we talk about roots of an equation. We talk about zeros of a function. Okay? But not really that big a deal, honestly. Okay, so here's what I want to know then. Starting off here. We've got some polynomial function, p of x, with rational coefficients. Okay, it has rational coefficients, so that means that irrational root theorem is going to apply, right? If we see any square roots in our zeros, they're going to be parts of conjugates, conjugate pairs. Okay, so they tell us 2 zeros. Here's one of them. 17 minus the square root of 6, and it's got a multiplicity of 1. It only shows up once. And the other one we see is negative 2i. Can anybody tell me another zero that's implied by this? They only gave us 2, but there might be more. What's another one? There you go. Exactly, right? Because we have a 0 with a square root in it, it has to be part of a conjugate pair. If we get 17 minus the square root of 6, then 17 plus the square root of 6 is also a 0. Okay, what about this negative 2i? Are there any other implied zeros that must go with that? Plus 2i, right? Because we also know that any non-real zeros always come in complex conjugate pairs. And minus 2i is the same thing as saying 0 minus 2i, where the real part is 0 and the imaginary part is 2. Well, that must go with 0 plus 2i, right? Those are a complex conjugate pair. So yeah, we also get positive 2i. Now, each of those zeros has a multiplicity of 1. So what's the total multiplicity of the entire polynomial? It's going to be 4, which means that this must correspond to at least a 4th degree polynomial. And maybe there's some other zeros that they didn't tell us about. Maybe 5 is a 0 or something, right? But it doesn't need to be. It's not implied. But if those two numbers are zeros, then it has to be at least a 4th degree polynomial. That's the smallest it could be. Okay, give me thumbs on that. Does that make sense? Okay, all right, good. All right, so there's one type of question you're going to see. If I give you some zeros, fill in the blanks. What are the other zeros that could go with those? Okay, here's another kind. This time we're going to build a polynomial that has this stuff included. Find a polynomial equation of least possible degree, so the smallest possible degree, with integer coefficients, and integers are rational numbers, aren't they? Right? Integer coefficients having a greatest common factor of 1, that's not a big deal, and whose roots include the numbers 0, 3, and negative 5. Okay? So we're talking about an equation, some polynomial being equal to 0. So we said roots, but we could talk about the zeros of the polynomial. Remember, interchangeable. Okay, so what about this then? If the zeros are x equals 0, x equals 3, let's color code this, 0, 3, and negative 5, each with a multiplicity of 1, let's say. Okay, because we want to make this as small as possible. So we're going to have a 3rd degree polynomial that we're going to build. How could I build that polynomial? Okay, and this goes back to that factor theorem we were just talking about on the last page. If k is a 0, or just k is some number, then x minus k is the factor that goes with that 0. Okay, so then if 0, x equals 0 is a 0, what's the factor that goes with that? What about 3? If 3 is a 0, what's the factor that goes with 3? No. Let's look back at this again here. So if k is some number, right? Let's call k 7, right? If 7 is a 0, then x minus 7 is a factor. Has to be, right? Because think about the zero product property. How do we get the zeros? We set each factor equal to 0 and solve, right? So there's always that correlation. You don't even have to really put a whole lot of thought into it. If whatever the number is, if I tell you it's a 0, then x minus that number is a factor of the polynomial, guaranteed. Okay? So again, if 3 is a 0, x equals 3, what's the factor that goes with that? X minus 3, right? What about 0? If 0 is a factor or is a 0, then what's the factor? X minus 0, which is just x, isn't it? Right? Okay, so we can start to build our polynomial then. We'll call it f of x. And the first factor is going to be just plain old x, right? Doesn't that make sense? Because if we were using the zero product property, we would ask ourselves, what's the value of x that makes x equal 0? Well, 0 does, right? Okay. Now, what about the orange one? 3. Well, that's going to be the factor x minus 3. What about negative 5? What's the factor that's going to be associated with negative 5? X minus negative 5, which is x plus 5. Exactly. X minus negative makes that a plus 5. There's our function. How about that? Okay, that's the simplest function we can build. Okay, make sense? Okay. So then all I would have to do if I wanted to build this, before we jump in any further, doesn't this make sense now? Just think about, let's just kind of test our work so far. If I were going to set this equal to 0, this function equal to 0, to find the zeros, well, these are the answers I would obviously get, right? The 0 of the yellow factor is 0. The 0 of the orange factor is 3. The 0 of the blue factor is negative 5, right? Everybody get that? Okay. And what is the meaning of a 0? Those are the values of x that make the function equal to 0. And we know that if I've got it written as a product of factors, the only way it can multiply to 0 is when I multiply by 0. So one of those three factors has to be 0 in order for the product to be 0. Okay, so then let's get rid of that. Now all we would have to do is just expand this thing out, right? Well, we can do that. Let's go ahead and what if we were to FOIL this stuff out first, right? So I've got this x out in front, and then if I distribute, x times x is x squared, x times 5, 5x, okay, negative 3 times x. So let's add those up. 5x plus negative 3x, 2x. And then finally, good. And if I multiply an x through, what's that doing? Yeah, it's just, okay, right, it's just increasing the power of x by 1 in each term, isn't it, if I distribute? And doesn't that just give me that for my answer? Okay. Give me 1 to 5. Does that make sense what we did there? Okay. All right, let's try another one. So that's kind of the game for the day. Find a polynomial function of lowest degree with rational coefficients that has the given numbers as sum of its zeros. Okay. Now, here's another thing we'll talk about this time. Assume the leading coefficient is 1. Leading coefficient means the number in front of the biggest power of x, right? Okay. Okay, so then they're telling us that those are our two zeros that they give us. Okay, so let's add those. We've got the square root of 3 and 3i. Are there any other implied zeros? They gave us 2. Are there any other zeros that we must also have? What's it going to be? Negative 3i is one of them, right? Because we know that those non-real zeros have to come in complex conjugate pairs. So 0 plus 3i, 0 minus 3i. What else? Negative square root of 3. Yeah. So I get 0 plus the square root of 3 and 0 minus the square root of 3. Okay. Now, each of those, we want to build the minimum degree. So each of those, we'll just say each of those has a multiplicity of 1. There's no reason for us to make it any bigger, right? Which tells us that the smallest polynomial that we could build with those two zeros is going to be a fourth degree polynomial, right? Okay, so what's going to happen then? If we want to build our polynomial, now here's where it really pays to kind of think about the process before you jump into it, because we can make the algebra a lot easier. So the factor I get from the 0 square root of 3 is what? Everybody, what am I going to get? If square root of 3 is a 0 of my function, what's the factor? I'm going to make up a new number, and I'm going to call it a Thetan is my new number. It's just I invented it. If Thetan is a 0 of my polynomial, what's the factor that goes with x equals Thetan? What's it going to be? X minus Thetan. Doesn't matter, right? It doesn't matter what the number is. Whatever the number is, x minus that is the factor that goes with it, right? So I'm going to get, I'm going to get x minus square root of 3 from this guy. What's the factor that goes with negative square root of 3? X plus square root of 3, which is the same as x minus negative square root of 3. What's the factor that goes with 3i? X minus 3i. And what's the factor that goes with negative 3i? Let's see, Mackenzie, what's going to be the factor that goes with negative 3i? X plus 3i, very good. X minus negative 3i, which is x plus 3i. Good. Okay, so there's our function. Now, what about the leading coefficient part? When I multiply all these out, would you agree that if I multiply, like when I distribute all this out, the leading term right now is going to be x times x times x times x. It's going to be x to the fourth, right? Because the leading term is just going to be the product of all the biggest terms in each individual factor, right? Okay, well, if I want the leading coefficient to be 1, then I don't need to multiply all this by anything. What if it said the leading coefficient is 7? What would I need to do? If I wanted the leading coefficient, so when I wrote this whole thing out, if I wanted to get f of x equals 7, x to the fourth, what would I have to do to get that 7 there? You know, I'm going to have a bunch of other stuff too, but what would I have to do? I'd have to add another little factor up here, constant factor, wouldn't I? I'd have to put a 7 out front, right? Because as of right now, I'm just going to get an x to the fourth. Everybody see that? Okay. So we could even talk about there being like, we could say, you know, a is going to be the leading coefficient when we build our polynomial from these zeros. And we're just going to let a be whatever we want the leading coefficient to be. Well, in this case, we want a to be 1. So it doesn't really change anything. If I wanted it to be 7, I'd have to put a 7 there. Okay? All right, so we just get a 1 there. Okay, and we multiply this whole thing out then. What's that going to give us? I've got 4 things to multiply together. What would be the smartest order to multiply those things in, do you think? What do you mean by that, Johnny? Okay, good. Perfect. Yeah, we want to multiply these in ways where we can take advantage of the fact that those are conjugates, right? Look, the orange factors are conjugates, and so are the blue ones. Let me remind you guys about something that we talked about a little while ago. Right? Didn't we say that if I multiply conjugates together, a plus b times a minus b, we get something simple? What was that? A squared minus b squared. If I multiply regular conjugates together, I get a squared minus b squared. It's just the difference of squares pattern, isn't it? Right? If I go in this direction, it's like the factoring pattern, the difference of squares, isn't it? But we're just doing it in reverse. Okay. Now, what was it if we multiplied complex conjugates together, not regular conjugates? What did that do? It changed things a little bit. And you can always just FOIL this out, but don't waste time. This is like, if you know these product patterns, it makes life so much easier. It was a squared plus b squared. Okay, so that's going to help us out a bunch. We're going to use Johnny's strategy here. So we've already got a 1 out front. We don't need to do anything with that. But if I multiply the orange stuff together, those conjugates, aren't I just going to get a squared minus b squared? Where a is x and b is the square root of 3, right? X squared minus the square root of 3 squared. And the square root of 3 squared is just 3, right? Everybody see that? Okay, now how about the blue ones? Those are complex conjugates, right? Where a is x and b is 3. So what's that going to give me? Plus 3 squared, yeah, plus 9, right? Everybody see that? Because of the i's, right? And how come that becomes a plus? Well, because what we really get here is a squared minus b squared times I squared, but I squared is -1. So it changes that negative to a plus, right? Okay. Now, this is no big deal, right? Now we've got this down to where all I have to do is multiply these two binomials, just FOIL them, right? No big deal. Okay, so we get f of x equals, if I distribute the x squared, what am I going to get? You guys walk me through this. X to the 4th plus 9x squared. So what's that? Plus 9x squared minus 3x squared. Oh, okay, good. Plus 6x squared. Done. There it is. And what's the leading coefficient? 1. Okay. Everybody see that? How about that? Okay. All right, let's try a little board work. This is good board work stuff. So go to the board and try this one. Find the polynomial of lowest degree with rational coefficients. We'll make things simple and say the leading coefficient is 1, and it's got to have those 3 zeros. There we go. This is more of like a bonus type question. You, at the end of the assignment, you're going to get a couple like 1-point questions, but do them. I mean, these are like, challenge yourself to do these. These are kind of cool problems. And on the test, probably same kind of thing. Probably be a problem or two like this that's going to be just for kind of bonus points, right? Same kind of problem we've been doing. Look, it says find a polynomial function of degree 3. So they're already telling us that, with real coefficients that satisfies the following conditions. The zeros are, and it tells us, the zeros are 0 and 1. It says I want to make degree 3, right? It tells me that the multiplicity of the 0 at x equals 1 is 2, right? Well, if I want this to add up to 3, then that must mean that the multiplicity of the 0 at 0 is 1, right? Okay. Okay, fair enough. So then let's build our polynomial. Okay, so what's the orange factor going to be? This could be x minus 0 is just x, right? So we're going to get x. What's the blue factor going to be? Okay, good. X minus 1, and it's going to be squared because the multiplicity is 2, right? Okay, but they didn't tell us what the leading coefficient is going to be this time. Everybody see that? Doesn't say. So the leading coefficient, I'm just going to call it A because I don't know what it is yet, right? We're going to have to figure it out. But they did give us a piece of information that's going to help us. They told us that f of 2 equals 12. What does that mean, f of 2 equals 12? Okay, if I put in 2 for x, I'm going to get 12 as the output of my function. Okay, so let's do that then. If I input 2, I'm going to get a times 2, right, is the value of that factor. What's the value of the blue factor going to be if I input a 2? Yeah, it's going to be 1 squared, which is just 1, right? Okay, but what's the output supposed to be? F of 2 needs to equal what? 12. Aha. That's got to equal 12. So that allows me to figure out what the leading coefficient needs to be, right? We just called it A because it was unknown, right? So we let it be a variable. We didn't know what that was going to be. But now we can figure it out. If I multiply all this stuff together, 1 squared is 1. So 2 times 1 times A is just 2A equals 12. So what's A? 6. So we know what A is. I can plug that back in up there, and then we get our function. F of x has to equal A. Actually, I'm plugging it in, not there. Sorry, I'm plugging it in, not there. I'm plugging it into my function, the actual original function, which is, let's pick a different. Oops, man, I'm having troubles here today. Right? I'm going to plug that value of A into the function, right? We just use this line here to calculate A. So I get f of x equals A, which is, we figured out is 6. Times x. I don't need parentheses around the x though, do I? Times the quantity x minus 1 squared. That's my function. That's it. Now, if I want to write that in standard form, I'd have to expand that whole thing out, right? Which we can do. This is good practice. Look at this part right here. You guys should be able to, from the Pascal's triangle stuff, you should be able to do that in your head. Here's why. Think about this expansion. A plus b squared is what? How many terms are going to be if I expand this? 3. Okay, good. Leading coefficient's always 1. So what's the first term going to be? A squared plus 2. Look, whatever that is, that's got to be, the exponent is always your second coefficient. So 2ab plus, got to end with a 1, b squared, right? So we know that pattern. That's a flashcard pattern. You just got to be quick with those. So what's this going to give us then? So a is x and b is -1. We'll use that pattern. So x minus 1 quantity squared is going to be, okay, a squared becomes x squared plus 2 times x times -1. 2 times a times b. What's that? 2 times x times -1. -2x. So I get x squared minus 2x plus negative 1 squared is 1. There you go. Okay, so I get six x times that. So I just distribute the 6x and we're done, right? So we end up with f of x equals, what's that going to be? 6x times x squared is 6x cubed. 6x times negative 2x. Oh, good. Negative 12x squared, and 6x times 1 plus 6x. There's our function. We got it. Look at that. Boom. Amazing. Okay. All right. Kind of a bonus one, but you guys got that. That's no problem. And then the last one. Okay, I'm going to show you something. And this is something, again, this is kind of a bonus type thing. I mean, if you don't get this 100%, don't panic. It's not like I'm going to have you guys do a bunch of this, but I teach this to the honors class. You guys can get this too. There's no reason you can't. So we're going to go through this. If 1 minus square root of 2 is a 0, what's the 0 that goes with that? 1 plus the square root of 2. Exactly. Okay, so those go together. We'll make that, those will be our orange zeros. If 2 plus 4i is a 0, what's another one? Okay. And so if I want to build a simple polynomial from this with a leading coefficient of 1, so we'll make that part simple, I'm just going to have to take the product of all those, right? So f of x is going to equal, now this is the part that you got to think about a little bit. If 1 minus the square root of 2 is a 0, what's the factor that goes with that? If k is a 0, what's the factor that goes with it? Okay, good. X minus k. In this case, k is going to be that whole thing, right? So I'm going to have x minus the whole 0. So I got to put it in parentheses. X minus 1 minus the square root of 2 times x minus the quantity 1 plus the square root of 2. Okay, same kind of thing over here, right? If 2, oh, okay, well, we'll get this one later. Good job today, everybody.